Our goal for today is we know now how to find slant asymptotes and when slant asymptotes happen. We talked about that last Thursday. Our goal for today is can we now graph with slant asymptotes? So this was the example that we did last Thursday in class. And we went ahead and we started by saying, well, we are in pre-calculus, so we know we would start every rational function with factoring because we know about wholes. So we factored, and we used factored by grouping in the numerator. You can look back at your last Thursday's notes if you need to, but we got x squared minus 2 and x plus 2 for factors. And then we did x plus 2 and x plus 1 in the denominator. So we did on Thursday mark out the common factor of x plus 2, and we said there is a whole. And we kind of talked about, okay, we could go through and we could find the whole, but we didn't actually write that down. So today, because we're going to graph with a slant asymptote, we need to know where that whole is. So I'm going to write down my whole as a characteristic for my graph. Remember that the whole happens at the zero of this canceled factor. So if your factor is x plus 2, set that equal to 0, x equals negative 2. So the whole is happening at negative 2 for x. To find the y-coordinate of your whole, plug that value into the reduced function. So that would be x squared minus 2 over x plus 1. Okay, so for my y value, I'm going to do negative 2 squared minus 2 in the numerator and negative 2 plus 1 in the denominator. I'm plugging into the reduced function. That's 4 minus 2 or 2. Negative 2 negative 2 plus 1 is negative 1. So the y-coordinate of my whole is also at negative 2. Now, I could, if I wanted to, graph as I go along. So then I could go left 2 and down 2, and there's a whole. You can consider that one point on your graph, so it will help you determine where your graph is going to be. Okay. Now, the next thing I usually do after I look for holes is I start with my asymptotes, because that kind of just breaks up my coordinate plane. So I usually do the vertical asymptote next. It doesn't matter what order you do these things. For the vertical asymptote, if you refer back to your notes from last Wednesday, it says set your denominator equal to 0. So we have two factors in the denominator when we factored x plus 2, x plus 1. But because x plus 2 was canceled for the whole, it's no longer in the running for a vertical asymptote, right? So we only have one vertical asymptote at the 0 of x plus 1. So our vertical asymptote is at x equals negative 1. It is possible to have two vertical asymptotes. I think on the back side of the worksheet, we've got an example with two vertical asymptotes. So it is possible that you could not cancel a factor and be left with two vertical asymptotes. That's fine. I'm going to plot that at x equals negative 1, right over here. Okay. Let's see. Now, if this was a regular problem, and we already know what's going to happen because we did it last Thursday, but if this were a regular problem, the next thing I would do is look for my horizontal asymptote. So for my horizontal asymptote, I'm comparing the degrees of the numerator and the denominator. Now, I can do that in the original function, or I can do it in my reduced function. In either function, I can see that the degree of the numerator is bigger than the degree of the denominator. So I'm going to say degree of the numerator is greater than degree of denominator. Therefore, horizontal asymptote does not exist. So I'm running through this like I don't know what's already going to happen, right? Remember that that's the case we talked about last Thursday. If the horizontal asymptote doesn't exist, there is a possibility that there is a slant asymptote. How do you know when to test for the slant asymptote? What has to be true about the degrees of the numerator and denominator? Tyler? The degree of the numerator is exactly one more than the degree of the denominator. Because then when we divide, we'll get something that's linear, right? X cubed divided by x squared, x to the fourth divided by x cubed. That's a linear thing, and that would be a slanted line. There's our slant asymptote. So we see that whether you're looking at the original, the cubic divided by quadratic, or you're looking at your reduced function, x squared minus 2 over x plus 1, in either of those, the degree of the numerator is exactly 1 more than the degree of the denominator. So we have a slant asymptote. Okay. Now, I think last Thursday, I did the slant asymptote as a synthetic division on this problem. Just to kind of review slant asymptote, because it's been 3 days, I'm going to real quickly do my slant asymptote as a long division. So I'm going to use the reduced function, x squared plus 0x minus 2. And I'm dividing it by x plus 1. If I were to do that division, I would start with the first terms. X squared divided by x is x. Multiply that through the divisor, x squared plus x. And then I'm subtracting all of that, so that's going to be minus minus. And then I get negative x minus 2. Well, negative x divided by x is negative 1. And I've hit the end of my quotient, right? Everything else that I would do after that is for remainder purposes. And the slant asymptote is the quotient with no remainder. So I know that the slant asymptote is y equals x minus 1. And we had done that with synthetic division in our notes on Thursday. So you can do synthetic when appropriate or long division. You'll get the same answer for your slant asymptote. Now, in terms of graphing the slant asymptote, you then have to be able to graph a line, right? Plot your y-intercept, negative 1. So I would go down 1. And then your slope is a positive 1. So I'd be going like up 1, right 1, up 1, right 1. So something like this. There's my slant asymptote. Okay, before I leave the asymptotes, is everybody okay with what we've done so far? Does anybody have any questions? Okay, after holes and asymptotes, the rest of your work is really about trying to figure out the points on the graph so you can draw an accurate graph. I always recommend trying to look for intercepts because those are easy points to find. So you could go to a table of values, but you can also look for intercepts here. If I were to do a y-intercept, I would be plugging 0 in for x. You can do that in the original function. You can do that in the reduced function. In either of those, you're going to get negative 2 over 1, which is negative 2. So I have a y-intercept at negative 2, and I can plot that point on the y-axis. For the x-intercepts, does anybody remember our shortcut for x-intercepts in rational functions? Set the numerator equal to 0. In a fraction, the only way that the y value, the fraction, would equal 0 is if the numerator is equal to 0, right? 0 divided by a number. So we can just set the numerator equal to 0. I would use my reduced function, x squared minus 2 equals 0. Add 2, square root. Anytime you square root, add a plus or minus. And we must have x-intercepts at 2 spots. Positive square root 2 comma 0 and negative square root 2 comma 0. So if I'm writing out my intercepts, they should be written as ordered pairs. And in order for you to graph that, just think about like where is the square root of 2? Without a calculator.
Greater than 1.
Bigger than 1.
Less than 2.
Less than 2, right? It's in between the square root of 1 and the square root of 4. So if you know it exactly, it's 1.4. But all I'm going to be checking for on the graph is that it's in between 1 and 2. That's where the square root of 2 is, right? Those are on the x-axis. Now, you can decide after that if you need more points. Some people may say, oh, the hole in the intercepts, I've got enough points and I can see what the graph is doing. Some people may say, I'm not really sure. I've never graphed with a slant asymptote before, so I want to check and see. So maybe I'll try negative 3 just to see where the point is. I'd plug it into my reduced function, y equals negative 3 squared minus 2 all over negative 3 plus 1. So that's 9 minus 2, which is 7. Negative 3 plus 1 is negative 2. So if I go left 3, I should go down 3.5. Okay. So left 3, down 3.5, something like this. And that kind of confirms what I thought. I'm just getting like really close to my slant asymptote. So I can sketch what I think is happening. It's going to come close to my vertical asymptote there. It must make a bend, and it should be kind of curvy right there. Okay. So that's what that side looks like. And on the other side, if I need an extra point, I can find an extra point, but probably the same thing is going to happen, right? It's going to get closer to my asymptotes. Okay. So then I can sketch what that might look like. There you go. Now, I will only ask you about domains with slant asymptotes. I'm going to talk more about that in just a second, but let's just look in terms of domain. What things need to be excluded from our domain for x? Can't put in negative 2, that gets us a hole. Can't put in negative 1, that gets us a vertical asymptote. Those are the two factors in the denominator. Okay. So for my domain, okay, running out of room up here, my domain, I'm going to do negative infinity to negative 2. That's where my hole is. In union with negative 2 to negative 1, that's where my vertical asymptote is. In union with negative 1 to infinity. So there's two places on the x-axis where no graph shows up. Once at the hole, once at the vertical asymptote. Now, technically on this problem, I could ask you about range. Okay. If I asked you about range on this, the lowest value that this graph will ever be is negative infinity. And then as we go up, there's a point at every other y value. Some people might look at the hole, but on the other branch, there's a value at negative 2. So negative 2 is included in the range. So this range would actually be negative infinity to infinity. It would be all real numbers by the way that the graph looks. The reason why I'm not going to ask you about range for slant asymptotes, I'm going to use green here, but don't draw this in your notes because it's not part of this picture. But sometimes, instead of the branches being where they are in this picture, your branches could look something like this in the skinnier portion. And if they look like that, if I were doing the range, I would start at negative infinity and I would come up to the maximum of this U shape. But I may not have found the maximum in my table of values. Like it could be at a weird point in between two nice values. So you actually need calculus in order to find that without a calculator. But I'm going to say do this without a calculator, and you don't have calculus. So I can't ask you about range. If I let you use your calculators, you could use the calculator function to find the min or the max, and then you could give me range. Okay? But if you were doing it, it would be like negative infinity to whatever that value is. You would skip a whole bunch of numbers, and you would pick up at a new value that is the minimum of that other u. Okay? But you cannot do that without a calculator. So fair warning. You are expected to do domain for slant asymptotes. I will not ask you about range for slant asymptotes. Okay. Does anybody have any questions, concerns that they want addressed? Okay, before we go on to our homework, just really quickly, I did plug this into my graphing calculator. So let me pull that up. Notice that in my y equals menu, when I put this function into my graphing calculator, I don't have that math print, so I don't like see a numerator and a denominator. If you're plugging rational functions into the calculator, you need a group of parentheses around your numerator and a group of parentheses around your denominator with a division sign in between them. So then the calculator knows this polynomial is on top, this polynomial is on bottom. And then if I were to go ahead and graph this, this is what my graph looks like. Okay, something similar to what we saw. If you wanted to, you could add in like a graph for x equals -1 or the line y equals x minus 1 so you could actually see the asymptotes there. What is your calculator not able to show you? The whole. So imagine this. If I let people use calculators on a quiz or a test like this, there'd be some people who would type that in, draw what they see, and move on. And they would never mark a hole for me. So I know we're all itching to use our calculators, but this is a good example where you'd be missing a really important characteristic of your graph if you used your calculator. So that's why sometimes I want you to do things without a calculator so we understand how the function works. Okay, can you find your pink sheet from Thursday?